So we have a pre-recording from the speakers, and we're going to get started right now. Thanks.
Hello everyone, thanks for coming, and I'm very honored and excited to be here to give a presentation. So today my topic is Safe Harbor or House of Waters, unveiling the hidden parts of the TorchScript engine in PyTorch. So here, let me briefly introduce ourselves, and we are all security engineers from Alibaba Cloud, and I'm Ji'an, and I complete this work together with my colleague Lishuo, and we were really looking forward to presenting in person, but unfortunately, due to visa application issue, we are unable to attend the event on site, and we sincerely apologize for this. And as a result, we have to share our presentations through a pre-recorded video instead. And if you have any questions, please feel free to contact us. So here, this is the agenda. So first is the introduction section, and after that, we will share where the story begins, and then I will analyze how it only works and introduce the TorchScript engine, and finally, I will share the impact of this vulnerability and share some defense recommendations and a summary. So first, introduction. And PyTorch is a machine learning framework based on Torch machine learning library, and it was developed by Facebook, and now it is an open source project. And it is very easy to use and has some really great features. And PyTorch is widely used in the fields of deep learning research, natural language processing or called NLP, and computer vision. But to be honest, in the field of machine learning, there are many popular frameworks and well-known projects like TensorFlow and Perils. But however, according to the Perils code website, and you can see that PyTorch has undoubtedly been the most popular machine learning framework. So if someone can find some bugs in such a famous AI framework, and that will be a really cool thing. And next, come to the second part, where it all began. And in the early days, PyTorch used pickle to load and save model for convenience. However, pickle is one of the most well-known security issues in Python, and in fact, the official Python document was that using pickle can be unsafe, especially when loading untrusted data. So in 2021, and someone raised an exception on GitHub and called for a solution to address the pickle issue in PyTorch. And finally, in 2022, PyTorch released a notable update introducing with-owning parameter. And let's briefly analyze the implementation of with-owning, and you can see that by default, with-owning is set to false, and it will use pickle to load the model. And if we set with-owning equal true, and you can see that it will use something called with-owning unpickler, and you can consider it as a restricted pickle. So now, let's try it out. So first, since by default the with-owning is false, and we will use pickle to load the model. So here we can easily create an evil model and use this reduce magic method. And you can see that after we save the model and we load this model, and you can see that we successfully execute the system command whoami, and we get the output root. And however, if we set with-owning equal true, and you can see that it just threw an exception, and it seems that the vulnerability is effectively mitigated. And also on the official PyTorch website, and you can see that they consider torch.load with-owning equal true is also secure. And they also warns that loading untrusted checkpoint with-owning equals false must never be done. And additionally, when similar security issues are discovered in other PyTorch-based components, and they often fix it by using with-owning equal true. And here is an example. So initially, VLM used torch.load without with-owning equal true, and which introduced a security risk. And they fix it by simply add the with-owning equal true parameter. And so not only VLM, and in general, whenever a software is found to be using torch.load without with-owning equal true, and the fix is also the same way, just adding the parameter. But here comes the question, can we blindly trust the security of with-owning? So next part, we will dive deeper into it, how with-owning actually works. And earlier we pointed out that with-owning is something like a restricted pickle. So before we analyze how with-owning is implemented, and we need to understand how pickle works. And pickle is something like an interpreter, and it reads and interprets each opcode in sequence and executing the corresponding operation. So for example, here we first encounter the global opcode, and it will use the load global function, and you can see that it will call font class and it will import this model. And so here after we execute this command, and you can see that it will get the system function and push it onto the stack. And since now we get the function and we need to get the arguments, and so here we can use the Unicode opcode to read the string, and so here we will get the while, and since arguments must be in turbo format and we need to wrap this string into a turbo, so we use this turbo1 opcode, and you can see that it will replace it with the turbo. And so here after execute the load turbo, and you can see that we wrap this string into a turbo, and now we get the function and its arguments. So now we can use the reduce opcode to execute this function. So here we use the reduce and it will execute the node reduce function, and you can see that it will get the arguments, get the function, and call it. So finally we can get command execution. So how does withholding address this issue? And through the above example, and we can roughly sense that the most dangerous part of the pickle deserialization is load global and load reduce. So the withholding and pickle just add some restriction to this dangerous opcode. Looking at the code, you can see that the load global function has some blacklist and whitelist. And also load reduce is restricted in a similar way, and it has a whitelist. And so in general, withholding is implemented using a whitelist and a blacklist. So how can we bypass? And a common approach is to analyze the whitelist and check whether there are any potential dangerous functions that could be exploited. And I did the same, but I didn't find anything useful in the end. And we are often limited by fixed ways of thinking. So for example, here in this case, most of us may only see the obvious whitelist and blacklist mechanism and stop here. But however, in reality, the loading process of torch.load with withholding equal true is quite complex. So is it possible that there might be some issues elsewhere in the loading process? So I try to conduct a complete analysis of the withholding workflow to ensure nothing is missed. So I started analyzing the entire torch.load process, and I step into the code and debugging the code line by line. And during one of my analysis, I noticed something very strange, and torch.g.load. So what is that? And I had no idea with this, so I just searched it on the Google, and the document just said that torch.g.load is something to use to load models in the TorchScript format. So now you can understand that why we name this topic. Yes, we will analyze and explore the TorchScript engine.
Hello everyone, this part will cover the basics of TorchScript and its code implementation. TorchScript is used for deploying model in environments without Python interpreter, such as CPP and mobile. It can be compiled from Python code through scripting or tracing, and save as PT file, which can be loaded and run in CPP and mobile. The save and load process involve serialization. I will explain how Python code is compiled to TorchScript, the serialization and deserialization process, the structure of PT fields, and finally how it executes. First, we can use torch.get decorator to script one Python function to TorchScript. The steps to compile are first, press Python source code into a Python AST. Second, convert the Python AST to a GIT AST. Third, transform the GIT AST into an AR graph. The AR graph initially contains many unnecessary nodes, which are eliminated through optimization to make it more concise. Let's take a deep look about the compile process. Before we start, I need to show what is function and model in this context. You can see that one is a function, the other is a class. The scripting process for these two are somewhat different, so we will introduce them separately. Let's look at the function first. The compile process is handled within the script AMPL function. There are two main functions, getJITDef and getScriptCompile. The getJITDef function performs two main tasks. First, it uses the AST library to convert Python code into a Python AST. And second, it calls build-def to transform that Python AST into a self-implemented JIT-AST. JIT script compile is a function bound from CPP to Python. With its implementation in the CPP layer, it further converts the JIT-AST to IR within the CPP code. It eventually invokes the toIR function, which finishes the transformation from JIT-AST to IR. Additionally, toIR also calls some optimization functions to simplify the IR graph. Now the function compile process is done. A high-level understanding of the process is enough for this sharing. If you are interested in the compile source code details, you can use the code stack I have provided to navigate through the source code. Then let's look at the model. The overall process is similar to that of functions. Expect there is an additional step at the beginning, retrieving all functions from the model. It needs retrieve functions and compile functions one by one. The stub fn function is responsible for handling this. Stubs fn is analyzed for infer methods to compile in this connect. Let's see what the infer methods to compile function does. In the infer methods to compile function, it first uses dir to get all attributes and methods of the model. After filtering, it saves the methods that need to be exported, thereby collecting all functions in the model that require compilation. Make stub from method converts the collected functions into JIT-AST using the getJITDef function, which is the same one used during function compilation. Back to create a script model AMPL. The method stubs variable stores the JIT-AST we just converted, and the create methods and properties from stubs function takes two method stubs as input and is responsible for converting it to IR. We can see that this code stack is similar to the code stack for function compilation. Both eventually finish the conversion into IR function. Now the model compile process is done. Overall, some key steps are the same as for function. Both use getJITDef to convert Python to JIT-AST, then convert it to IR through toIR. The serialization feature can save models and deploy them to other environments. Use TorchScript to save model as a PD file. Use torch.load to load the PD file as a model. The Python code here is converted from IR. You will notice it's slightly different than the original code. Let's see how script function script model is serialized. Script function has an additional step compared to script model. It needs to be converted to script model first. After that, both call serialize for serialization. During the serialization process, some information is stored in the data pickle and constants pickle in pickle format. Additionally, it saves the Python code converted from IR and debug info to the code folder. To summarize the save process, for touch function, first convert it to touch model. The remaining process is a sim. First, the value corresponding to the model is serialized in pickle format as data pickle. Second, obtain code and debug info via Python prints and write to code directory. Third, save tensor constants to constants pkl. Now the serialization is done. Let's look at the detail of the PT field. The PT field is compressed achieved using zip compression. The field tree after decompression is shown above, and we can use pickle tools to disassemble it. Above is the disassembled output of data pkl. The meaning of this pickle code is create an object named touch placeholder model and set its training attribute to true. And the touch placeholder model object is a secret model. So when interpreting data pkl, secret model object is created. The constants pkl contains pickle code, which can create a value object with tensor. The touch py field contains Python code strings. It's the same as the content of the code attribute in secret model because they are obtained in the same way. Okay, now we understand the three most important parts saved in the serialized field. Data pkl, constants pkl, and the source code in the code directory. Let's see how these parts are restored into a secret model. We can see that in the deserialized function, the three main parts of the serialized field are converted into a secret model. Let's look at the function implementation. Deserialize will call read_achieve to read constants pkl and data pkl. Then we'll get one model in CPP, which is secret model in Python. During the deserialization process, first unpicking constants pkl to obtain tensor constants, then saved in constants table. Second, unpicking data pkl during the process of unpicking data pkl. Relevant source code is read from the code directory and pressed as needed, and related constants are also read from the constants table. The code pressing process includes converting Python code to custom tokens and then transforming tokens into GIT-ST and finally into IR. This process differs significantly from the earlier Python to TorchScript compilation. To summarize the load process, first, reach main logic via deserialize. Second, call read_achieve to read constants pkl. Convert constants to values by unpicking and save them to constants table. Third, call read_achieve to read data pkl. Restore corresponding values by unpicking. Fourth, during data pkl unpicking, source importer reads code fields and constants table to restore IR through press tab to find named type to import named type. Now the deserialization is done. Let's take a look at how TorchScript is running. The IR graph contains of many nodes, and every node contains three parts: in, output, and opcode. Opcode is the key to execution. The process of executing TorchScript is is to iterate through the AR and convert it into instructions, then interpret the instructions. Every instruction has one OP code. There is a switch table here that finds the corresponding process logic through the OP and then executes it. Now we have a basic understanding of the TorchScript workflow. While reading the code, I discovered something interesting. There is one OP code named OP, and it can do a call on operator table. And the operator table contains many functions corresponding to operators. I'm curious about what operators they are. Some built-in functions register themselves as operators, requiring OP instructions to call corresponding functions. And the register operators class manages these operators and register them by register operator function. I patch the PyTorch code and add one function to output all operators. You can see there are over 2,000 operators here. Are all these operators safe? During our code audit of these operators, we discovered two interesting operators, save and from fill. Here we can see the corresponding implementations of these two functions. The save function will save specified value as a model to specified field. This can lead to arbitrary field write. But the saved field contains a lot of dirty data, which model information. The from field function will read the field which I specified. And convert the field content to tensor, then return the tensor. We can get the field content from the tensor. Now we know these two operators have vulnerabilities. But there is still a problem: how to call them from TorchScript. To get the answer, we need to first understand the operator registration process. The get built-in table function registers some object member functions to built-in ops. And during this process, it also adds prefix to the member functions for rename. Finally, the address of these functions and their modified names will be placed into built-in table. During the TorchScript compilation process, two sugar value will be triggered, where it checks whether the Python object exists in built-in table. If it exists, it returns a built-in function. Finally, this built-in function will be inserted into the AR graph through emit built-in call. Back to the built-in registration process. We now understand that item save may come from one of these objects in models containing built-ins. By testing each object individually for the presence of a save function, we will find that the save function exists in the touch object. Item from field can also be obtained in the same way. So we just need to call touch save or touch from field to get arbitrary field read-write ability in TorchScript. Now we can try writing a field to get RCE, but since there are some dirty characters, only specified special fields will work. The Ubuntu call type failed because of a permission mismatch. Our script uses touch save, which writes a field with 644 permissions, but the colon daemon requires 600 permission. Here is one poke video. Okay, you can see we get RCE. The vulnerabilities we have discussed so far might be more similar to logic vulnerabilities. On the other hand, some hackers may prefer memory-related vulnerabilities. We have also discovered a few overflow issues. Here you can see that when we load this model PT field, it triggers a heap overflow. As a result, we can observe that heap address and the loaded address of the library are leaks. This is one poke video. Okay, you can see we get RCE by memory bug. But due to time limited, we won't go into them in great detail here. We hope to share them in the future. This is the full details of this CVE. The fix is also relatively simple. It prevents the use of TorchScript when voice only is enabled.
So what is the impact of this vulnerability? The entire AI ecosystem is just like this house, and PyTorch is one of the fundamental components. And if there is an issue within PyTorch, just like we have removed one of the bottom level components, and the entire AI ecosystem is then compromised. And we did a simple search on GitHub for projects using this only equal true, and we can see that in fact many projects using it is this way. And here we select two well-known projects as an example to illustrate the impact of this vulnerability. And one is VLM and the other is transformers. And VLM is a high-performance library for efficient large language model inference and optimized for speed and memory usage. And so why did I choose it? And because it had a CVE number, and you can see that it used torch.load function and the withholding parameter is default value false, so it has an RCE vulnerability. And the fix way is very simple, just as a withholding parameter, and this seems to solve the problem, but because of the PyTorch issue, all mitigation ends up being ineffectively. And the safe harbor you once saw was actually also waters. And at the same time, I found a very interesting phenomenon, and you can see that when I check its requirements CPU.txt, and you can see that it just hard-coded the torch version. And also in the GPU version, and you can see that it also hard-coded the torch version. So what does this mean? It means that even if PyTorch released a new patched version, and users of VLM cannot update it timely because VLM has hard-coded the version. So as a result, the users will remain exposed to this vulnerability for a long period. And so now let's set up the environment. Since the latest VLM has already patched this issue, so we need to install old version and exactly 0.7.3, and you can see that when you install VLM, then it will install the exact version of Torch. And so here we will use this function as an example to illustrate the existence of the vulnerability. And at first, I didn't think too much about that. I just want to take the poke from the previous vulnerability and just hoping for one should succeed. And you can see that finally, we will definitely enter the logic we want, and it will load our evil model. So we will succeed. But it failed, and you can see that we don't create this field. So why? And let's take a look at the previous poke, and you can see that after we use torch.load to load this model, and we need to call the model to invoke the model and in order to trigger this forward logic. But here you can see that after we load this evil model, and it didn't invoke the model, it just fetched the items and then deleted the model. So this model was not invoked. And is it really end? And at that point, I noticed the error message, and it said that the model don't have the attribute items. And this error message gave me some inspiration. And items is essentially a keyword in Python, and it used to iterate the dictionary type object. So you can see that in fact, items is a function. So here, can we spoof the function name? And so here I just try for the first time, and you can see that I changed the function name from forward to item, and just run the code, and you can see that why it is still saying that our model don't have the items attribute. And but if we write in this way, and you can see that we just call the items function in our forward logic, and we run a code, and you can see that we successfully create a field, and this means we succeed. And this is very strange, and the reason is that when retrieving models functions, it determines whether these functions need to be exported. For functions not decorated as exports, and a lazy export strategy is adopted, meaning that they are only exported if called within the exported function. So here you can see that in the left picture, we just decorated our items function with exported. So here it will export the items function, and we can get this item attribute. And in the right picture, and you can see that since we call it in our exported function forward, and our object will also have this items function. And so finally, we report the vulnerability to the VRM official team, and who highly acknowledge our work. And you can see that it is very interesting since PyTorch document claims it is safe. And the patch is very simple, just change this version. And next, transformers. Transformers is a popular open source library by Hugging Face and provided pre-trained models and tools for natural language processing tasks use transformer-based architecture. And transformers also implementing some security hardening measures. For example, here you can see that it just used return equal true to load the model. And so now we set our environment, and you can see that since the latest version of transformers also fixes this issue, and we need to install an old version 4.51.3. And here this is the official document example from transformers, and you can see that we need to load the model from our Hugging Face and create a pipeline, and then we can create our conversation. So here, for example, we just ask a question, the secret to baking a really good cake is, and you can see that just give me some answer. And here this is my demo project, and you can see that we only have 3 fields, readme, config.json, and a test PyTorch field, and don't contain any evil code. And if we run the code, and you can see that it will use torch.load to load our remote PyTorch model. And let me introduce this code, and when we load a remote Hugging Face repo, and it will load this model, and by default, fields in zip tensors or PyTorch is allowed. And just like the previous VRM vulnerability, and it will call the keys function. So we can just change the function from items to keys, and we save the project in our local repo. And of course, if we run this code, and you can see that we can exploit, and we can create this field. And after that, we just report this vulnerability to Hugging Face, and you can see that it just patch it. And the patch is also very simple. You can see that it just checks torch load is safe. It checks the torch version greater or equal than 2.6. And finally, it defense and summary. So now if you are still using an old version of PyTorch, please update. And here is also some recommendations. So for example, from the model format perspective, we should use more secure format like zip tensors. And also from the model community perspective, and we should scan and flag malicious models, and Hugging Face has already done the relevant work. And also from the user perspective, we should not load untrusted models, and it is better to load them in the sandbox. So any questions? And thanks again for listening, and if you have any questions, please feel free to contact us at any time.